How do you choose filter types for digital signal analysis? Imagine trying to listen to your favorite song, but there's a lot of background noise. Filters help clean up signals so you can hear what really matters. When working with digital signals, picking the right filter is key. It all depends on what you want to do with the signal. First, think about the kind of frequencies you need to pass or block. Low-pass filters let signals below a certain point through, which is great for removing high-frequency noise. High-pass filters do the opposite, blocking low frequencies to eliminate drift or slow changes. Bandpass filters focus on a specific range of frequencies, perfect for isolating a particular signal band. And notch filters are used to cut out a narrow band of interference, like power line noise at 60 Hz. Next, consider the type of digital filter. Finite impulse response filters have a limited response time and do not use feedback, making them stable and good for applications where phase linearity is important, like audio or data transmission. Infinite impulse response filters use feedback, so they can achieve sharper frequency cuts with fewer calculations. But they can be less stable and might distort the phase of your signal. You also need to think about how sharply the filter separates the frequencies. Some filters have a gentle slope, while others have a steep cutoff. The sharper the cutoff, the more precisely you can isolate signals. Phase response is another factor. If your application needs the waveform to stay intact without distortion, linear phase filters are your best choice. Computational complexity matters too. Finite impulse response filters usually requiring more calculations, which can slow down real-time processing. Infinite impulse response filters are more efficient but need careful design to stay stable. The delay introduced by the filter is also important, especially in real-time systems where timing is critical. Your specific goal influences your choice. For noise reduction, low-pass filters are common because they smooth out rapid changes. In communication systems, bandpass filters help isolate channels. For spectral analysis, filters with sharp cutoffs and minimal ripple are preferred. Implementation details can limit your options. Hardware might restrict the filter order or complexity. The sampling rate and signal bandwidth determine the cutoff frequencies you set, and quantization effects can impact how accurately your filter performs. There are also special types of filters used in radio frequency applications, like surface acoustic wave or bulk acoustic wave filters, but these are mostly analog. Digital filters are favored in digital signal analysis because they offer flexibility, precision, and easier adjustments. In the end, choosing the right filter type is about matching the filter's frequency and phase response to your signal's characteristics and your analysis goals. If you need a stable, linear phase response, go with finite impulse response filters. If you want efficiency and sharper cuts, infinite impulse response filters are often better. It all comes down to what you want to achieve: noise reduction, signal extraction, or interference rejection, within the framework of digital signal processing in electrical engineering.